these notes. What we're going to do, we're going to go over a few things about this, okay? We talked about the fundamental identities. So you had to memorize these, but remember, you have a note card, and you also don't have to memorize all of them if you don't want to, okay? We talked about different questions that involve these identities, and I think where we left off were questions that looked like this, where we had some sort of expression, and we were asked to write it as an integer, okay? What this means is, sorry. What this means, no, it's fine.
No, I love this class.
No, you're totally fine. Sometimes I feel like doing that during my class, so. All right, so we have the expression. All it's asking us to do is simplify it, and it's giving us a hint that our answer is going to be like a number. Don't feel embarrassed, Shannon. Okay. Okay, and remember, there's like specific tricks for these sort of examples. The trick here is to start with a Pythagorean identity and do stuff to both sides until we get something that looks like the question on one side and the number will be on the other side, okay? This example in particular, we started out with an identity that both had cotangent and cosecant. We solved for, to make one side look like the question, and then we multiplied everything by 4 because we had 4s on everything, okay? Do you guys feel confident on trying example 9?
Yes.
All right, I'll give you a few seconds to do this one. It's a little bit easier than example 8. And we'll come back in a little bit. Come back to the front here. All right, this one was a little bit different because we started with sine and cosine instead of like any other weird ones. So it was a little bit easier. Sam, do you want to take this one away?
Yeah, so I noticed that the Pythagorean identity already has what the problem is.
Mhm.
So you just have to figure out, based on what's in front of the sine and cosine, what the number is going to be. So you just multiply it by 5.
Perfect. Multiply by 5, we get 5. Just a tip on WebAssign, if you're typing this in, don't type in this whole thing. All you need to do is type in number 5. That's all you need to do. Okay. Any questions on example number 9? All right. So that pretty much finishes up the notes for the fundamental identities. I really like that set of notes, but if you're starting out, you might be a little bit scared, and I understand that. But we're actually going to go to something a little bit more familiar. Okay. So I'm going to pass out a new set of guided notes. All right. Okay, so these are our guided notes. So let me just talk about where we're going here, okay? We've done a lot of stuff with sine, cosine, and tangent in particular. And I think when we started talking about these guys, we talked about them in terms of the right triangle, right? We had SOHCAHTOA, and for any acute angle, we were able to use the right triangle to find sine, cosine, and tangent of a specific acute angle on that triangle, okay? After we did that, we moved on to representing sine, cosine, and tangent using a geometric figure. What was that figure? Unit circle, good, right? And this was really useful in different ways, right? First of all, it was useful because we didn't have to have an acute angle to measure an angle. We could expand to like 120 degrees and 4 pi over 3. So we had more angles to find the sine, cosine, and tangent of. And it was also useful because we could also find the sine, cosine, and tangent of what I call boundary values, which were along the x and y axis, right? We could find the sine of 90 degrees and pi and 3 pi over 2, which aren't technically like acute angles or anything we can draw a right triangle on, okay? We did that by saying, okay, sine is the y value, cosine is the x value, and it was pretty easy to look at our circle and be like, cool, that's the sine of cosine, okay? I'm going to show you a third way of how to visualize sine, cosine, and tangent, and this is a little bit more familiar, okay? we're gonna represent these as functions or graphs of things, okay? And you're also going to have to memorize what these graphs of these functions look like, okay? What we're gonna do is we'll start out with sine, we'll talk about cosine, we'll talk a little bit about tangent, and then we'll take our quiz, okay? So whenever we have a function, we can base it on, well, theta or x and y values, right? We can make an x and y chart. Okay, taking a look at this function here, we don't have an x anymore, we have theta, okay? We can just kind of treat it as x and y, but just in our mind say theta instead of x, okay? When I graph this, since we don't have an x, I'm gonna make this a theta axis, okay? And I'm gonna make the vertical axis still the y-axis, okay? So instead of x and y, we have theta and y, okay? And I didn't label the x-axis yet. And let's say I just wanna fit the entire unit circle in this graph, okay? So I want this to go from 0 to 2 pi, okay? 0, our last y value should be 2 pi. What do you think the different markings should represent then? Yeah, pi over 2, pi, 3 pi over 2, right? We're cutting the unit circle into quarters, right? So this guy here is going to be pi over 2. This one's going to be pi and 3 pi over 2. Okay. Next, if we go backwards to negative angles, well, all we have to do is repeat what we wrote, but go in the negative direction. So on the left-hand side, this can be negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. Okay. So I've just labeled my x-axis. Now let's label the y-axis, okay? What do you think the highest value on the y-axis is going to be? 1, right? Because let's take a look at our unit circle. We have values of x and y, which are our sine and cosine values. And it looks like the furthest out we can go is 1, right? So what I'm going to do here, I guess you can make the very top one be 1. I'm actually going to make the second one be 1 because it looks a little bit prettier when you take the second one equal to 1. So I'm going to make 2 boxes equal the height of 1. And I guess that makes the negative version be negative. So I've just labeled my x-axis, I've labeled the y-axis, okay? Let's see if we can plot some values. Okay. The way I like to do this is just make an x and y chart, or in this case, a theta and y chart, right? Okay, and I'll plug in some values for theta and see what happens. Okay, now negative values we don't really like, so let's just do the positive ones. Okay, when theta equals 0, well, y would be the sine of 0, right? What's the sine of 0? Take a look. 0, good. Taking a look at your unit circle, the coordinate is 1, 0. Sine is the y value, so sine of 0 is 0. Okay, so it looks like we have a point on our graph, which is 0, 0. Okay. Next, pi over 2. Y would be the sine of pi over 2. Remember, that's our 90-degree angle. What's the sine of pi over 2? 0, 1, right? The coordinate for pi over 2 is, 0, 1. Sine is the y value, so sine of pi over 2 is 1. Okay, so it looks like our second point on this graph is going to be pi over 2, comma, 1. Make a little dot there. Okay. Next we have, pi. What's the sine of pi? Good, 0. Okay, so we have another point, pi comma 0. Next, going to 3 pi over 2. Sine of 3 pi over 2 is -1, good. So that's another point under 3 pi over 2. And going back to 2 pi, that's the same as sine of 0. So yes, 0. Good. Okay. So what I have here, I have 5 points plotted on my graph. Okay. These are my important points, but it looks like I don't have enough detail yet because there's many ways we can connect the dots. Okay. One way that I don't want you to write down on your paper, okay, so don't write this down, is we could connect the dots like this with straight lines, right? We could go up, whoop, we could go down, didn't mean to do that, and we can go back up, okay? Now, I wish I had time to explain exactly why this is not the shape of the graph, but I feel like if you went back and tried to plot some more of the values like pi over 6, pi over 4, and pi over 3, you'll see that the graph isn't like a straight line graph. It actually looks like a curvy graph, okay? It's gonna look like we have parabolas between each of the high values and low values. Let me show you what I mean by this, okay? So it's gonna look like we have a parabola between 0 and pi. It kind of curves up and curves back down, okay? And the same thing happens in the negative side. So we go down, curving toward the top or the bottom point and curving back up, okay? So sine and cosine, their shapes are more curvy. You kind of flow from 0 up to 1, going back down to -1, and you kind of turn back around to get to 2 pi. Okay. Any questions so far? Okay. Now, remember, we don't just have angles between 0 and 2 pi. We have negative angles. We have angles that are bigger than 2 pi. And I guess I could go and like plot these and use my X and Y chart to do that. I'm gonna tell you I don't have to though. Anyone know why? Yeah, it reflects over. And the reason for that is we have a unit circle. Circles repeat, right? If we go around the circle once and we go around it again, it's just going to keep repeating the same values over and over and over again. So this graph that I drew right now, between 0 and 2 pi, we call this a periodic function, which means it repeats over and over and over again. And every time we go from 0 to 2 pi, and then 2 pi to 4 pi, right? And 4 pi to 8 pi, we're just going to repeat the same pattern over and over and over again. Okay, you don't have to draw this, but it's going to look like this, right? It's going to keep going on and on and on forever. Now, I'm going to erase that because it doesn't look nice. Okay, in the negative direction, it's going to do the same thing, but backwards, right? And I don't like drawing backwards, so I'm just going to start at -2 pi, which is a full circle in the backwards direction. And I'm just going to copy the graph. Oh my goodness, that's awful. Okay. Okay. So basically this graph is a repeating cycle of something going up and down and up and down. Okay. Any questions on this graph? Okay. Now, let me tell you something important, okay? These are the important things I want you to focus on when you graph this on a test or a quiz, okay? So, important things I want you to look out for. Okay, I want you to label the x-axis, specifically the positive x-axis, okay? If you don't feel like labeling the -1, totally fine. I am looking for these x values there, okay? I want you to label the y-axis. So I'm looking for -1 and +1. And the next thing I'm looking for is 5 important points, okay? Here, 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 and here. Okay, I want those points very clearly marked on the graph, okay? The final thing I'm looking for is I want the shape to look like a curvy graph, okay? I don't want straight lines connecting the points because, well, that's not what sine and cosine look like, okay? As long as you have these, I don't even know, couple of things, totally fine. If you don't even want to draw the negative direction, you don't have to, okay? As long as we have these specific things on the graph, you will get full credit, okay? Any questions on sine? Okay. I'm going to set you up for cosine, okay? when we graph cosine, I still want a theta and y-axis, okay? Cosine's very similar to sine, right? We're just looking at the x values. So I'm still gonna have the same y labels, okay? And I still wanna have the same x labels as well. So we're gonna have 0, pi over 2, pi, 3 pi over 2, 2 pi, okay? Going in the negative direction, we'll just have the negative values. Gosh. Okay. So when you set this up, you're gonna make your theta and y chart. Okay. And I'm gonna give you a minute to try drawing out the cosine, at least plot the important points, and we'll come back in a tiny bit. All right, let's come back together. I'm gonna go through this. So if you're still working, you can continue working, but let's write our chart out first. What did you get for the cosine of 0? 1, good. What about pi over 2? 0. Pi, -1. 3 pi over 2, 0, and 2 pi. Perfect. Okay, so I'm just gonna go ahead and plot these points. We go 1, 0, -1, 0, +1. Okay, nice. So when I graph this, it's not going to look like straight lines connecting each of the dots. We're going to make it look like a parabola going down, a parabola going up, and another parabola going down. Okay, so this is where you should have gotten, at least with the cosine. Okay, but cosine is pretty much the same as sine, right? We're just looking at a different value. So it's still going to repeat every 2 pi angles, right? We're still going to repeat just like just like sine did. And I guess if I wanted to draw the negative version, I could start at -2 pi, go down, and go back up to meet at the top. Okay. Finally, if we wanted to extend this even further, we could continue down on both sides, and it would kind of look like sine, right? So comparing these two, I guess cosine is sine, but it's kind of like placed differently on the graph, right? It's kind of like we took sine and we shifted it a little bit, maybe to the left by like 1 block, right? So very, very similar graphs, but they're kind of shifts of each other. Okay. So same thing with this sort of question. If I asked you to draw this on a test or quiz, I definitely want the labels on the x-axis. I want the labels on the y-axis, and I want these positive points made very clear. Also the shape of the graph. Okay. Any questions, cosine? Cool. All right, flipping over to tangent. We'll talk about this more on Monday, but I do want us to get set up here. Okay. When I draw my graph, I still want to label my x and y axis just the same as we did before. We'll talk about the y axis. You know what? Let's do the x axis first. Okay. So we have a theta and a y axis. And I'm going to label everything just as we did before. So 0, pi over 2, 3 pi over 2. Oh, sorry, pi over 2 pi. Oh. 3 pi over 2, 2 pi. And going in the negative direction, we'll just have the negative values. Negative pi over 2, negative pi, -3 pi over 2, and -2 pi. Okay. I'm gonna leave the y-axis alone for a bit. We'll talk about the y-axis, but our x-axis has been labeled. Okay. Next, let's talk about tangent. Okay. Before I talk about tangent by itself, can someone give me another way of writing tangent using an identity? Good. Tangent is sine over cosine. We identified tangent as the y value divided by the x value. The y value is sine. The x value is cosine. Okay. So it looks like if I took this function and just represented it a different way, this function would have a denominator, okay? Let me show you an example of a function that also had a denominator, okay? Anyone remember the graph of y equals 1 over x? What'd that look like? Yeah, perfect. So let me try to draw that out. It had an asymptote at the y-axis and at the x-axis, and it had these weird like things that got really, really, really close to the y and x-axis, right? So basically what we had is we had a denominator and we had at least a vertical asymptote. I know we had a horizontal asymptote at x equals 0, the x-axis, right? And this was because we can't divide by 0. So the division by x, well, at x equals 0, can't divide by 0. So that kind of made a vertical asymptote, okay? The same thing is going to happen with, oh my goodness, with tangent, okay? Except our denominator isn't x anymore, it's cosine of theta, okay? So what this is going to translate into, oh my goodness, we're going to have a vertical asymptote. Okay, and I'll tell you, there's no horizontal asymptote here. If you want to talk about why there's not a horizontal asymptote, come to my office hours, we'll talk about it. It's a little more complicated than the depth of this class, but we have a vertical asymptote whenever the denominator, or cosine of theta, is equal to 0. Does that make sense? Okay. So let's ask ourselves, well, when is cosine equal to 0, right? When is cosine equal to 0? Okay, well, what angles have cosine of that angle be 0? Ooh, pi over 2, 3 pi over 2, good, right? Cosine of pi over 2 is equal to 0. So pi over 2 is where cosine is equal to 0. And cosine of 3 pi over 2 is also equal to 0. Okay, so these are two examples of angles where cosine is equal to 0. Okay, well, this is a repeating sort of thing, right? Cosine goes on further than angles of 2 pi, below like negative angles. So I guess any like multiple of pi over 2 or 3 pi over 2 will also give us a a vertical asymptote, right? So for example, negative pi over 2, we have cosine being 0, negative 3 pi over 2 as cosine equal to 0. Okay. What this translates to is we know that tangent has a vertical asymptote at pi over 2. I'm going to represent that with a dotted line. Okay. It also has a vertical asymptote at 3 pi over 2. Okay. And going in the negative direction, we have negative pi over 2 and negative 3 pi over 2. Okay. Now, I bet we could even extend this further. If you want to, you can draw an asymptote every 2 blocks, right? So there probably is one here, right? You don't have to, but I'll draw it anyway. And 2 blocks in the negative direction get us this one, right? So it looks like tangent has this pattern of every time we go pi over from pi over 2, so every 2 blocks, we will have a vertical asymptote. Okay. Any questions so far? Good. Okay. Now let me add some detail. Okay. We talked about what happens at pi over 2, 3 pi over 2. Let's make a theta and y chart for the things that come in between. Yes. So we don't have anything at theta equals 0. So if I wanted to find the y value, this would be tangent of 0. What is the tangent of 0?
0.
0, good. Okay, so it looks like I have a point at 0, 0. Okay. Looks like pi's missing. What's the tangent of pi? 0, good. Okay, so pi 0 is our point. What about 2 pi? 0, good. And it seems like we have a 0 every single time we're in between, like right in the middle between the two asymptotes, right? So every time we have something in between these guys, we have tangent equals to 0. Okay. Now, one more thing I want to talk about is what happens when we have an asymptote? What does the graph do near an asymptote? Yeah, it gets closer and closer and closer to it, but it never touches it. Okay. So I'll talk about this more on Monday, but basically what tangent is going to do is on the right side, it's going to get closer and closer and closer to the asymptote. On the left-hand side, it's going to do the opposite, but in the negative direction. Okay, that's where we're going. I didn't draw it very well, so I'll redraw it next class. And I think we have a quiz to take.